Hello, students. Today we want to continue our discussion of equation solving. And we will use a lot of the ideas that we discussed in the previous lecture as we study the quadratic equation. The quadratic equation has a large role in STEM mathematics and also the quadratic function. So as you continue to study mathematics and your allied science courses, you will have plenty of experience with quadratics. So let's look at what we need to do today. I'll share my screen. What we plan to do is think about all of the different strategies that we can use to solve quadratics. And what I want to do is start with the idea of the so-called quadratic function, which in this case is going to be an integer polynomial. So I'm going to use some notation here that I haven't actually worked with formally, but we're just going to say this is a symbol for an expression that has the variable x. And later on, when we discuss functions formally, we'll lend much more detail to that. So in order to get started, there are several ways to solve quadratics. And one way that's very popular is through factoring and the zero product. So what I want to do is describe a method that I have written for factoring integer polynomials. And this probably has a lot to do with some methods that you had learned in your Algebra 1 and Algebra 2 classes, sometimes called the AC method, and I usually just call it the AC lemma. And I've just written this down formally so we can keep track of what's going on. So some new notation. The script Z here will denote integers or integral expressions. And we think of integers, ladies and gentlemen, we think of the natural numbers, 1, 2, 3, 4, etc. We think of adding the number 0 and all the additive inverses or all the negatives of the counting numbers as we see here. And then we just do the 3 dots, the ellipsis, to say that these numbers go on indefinitely. So you can get as small as you like with the negative numbers and as large as you like with the positive numbers, again, just focusing on integral values. Now, another thing that we're going to do when you think about the quadratic, just like we thought about the linear equation, instead of 2 constants, we're going to have 3. So what we're going to do is we're going to look at A, B, and C as integers and fixed. And remember, when we say a number or a variable is fixed, then its value is constant. So that's if you start out a theorem by saying alpha is fixed, that means the representation alpha has a value that never changes. So that's just a way of describing what we mean by constant, or you could just say they're constants. So we have the expression or function ax squared plus bx plus c. And this notation here just means integer polynomial. So we just append to the z here bracket x. And when we study our polynomials, we'll use more of this notation. So we want to try to build new notation as we move through the course so that we just don't get everything at one time. So little by little, I'll add the notation. Now, x will be the variable, and we won't restrict its value. It could be imaginary or real. And the idea is that we just say x is a complex number. So we know the complex numbers include not only the real numbers, but also the imaginary numbers. And in our next lecture, we'll have more to say about imaginary numbers. Additionally, the A, the B, and the C that are constant are what we call relatively prime. That means that the integer polynomial is termed primitive integer polynomial. So when you look at the A, the B, and the C, the only common positive divisor is just 1. So here, before I state the rest of the theorem, I just want to give you an example here. If you look at this integer polynomial, notice we have a 3, a 4, and a -4. Those are all integers from this set, as we know. But when we look for the greatest common divisor, that is, what is the largest positive divisor of all of these, that's integer, it is 1. Okay, so 3, 4, and -4 are relatively prime. So when we look at this quadratic polynomial here, we call it primitive. Now, you might be thinking, why do we really care about that? Well, let's think about what we do when we factor. If there are common factors in the coefficients, that's just extra hanging around that gets in the way. So what we would do is we would just factor that number and then divide it out. And then, of course, we have smaller coefficients. Now, the theory relies upon the polynomial being primitive. So not only is it important for theory, but it's important for just making the problem simpler. Smaller numbers will necessarily be easier than larger numbers. Now, how does the process work? I think you may see some similarities in what you have already done in your previous classes. So what we have is f factors in the integers. That is, we can factor this quadratic as the product of two first-degree polynomials if and only if we have the existence of two integers, and I'm going to call them z and w. Use any letters you like, but I have used z and w, such that when we multiply AC, that's where the AC part of the lemma comes from. We multiply AC, we find that that is equal to the product ZW. And then another important aspect is that the B, the coefficient of X, must be equal to the sum of Z and W. That is, when you add Z and W, you must retain the value B. Now, these are necessary and sufficient. So what we can do is we can just really focus on the part of the theorem that calls for us to find the Z and the W. So this is probably a method that you've talked about in some of your earlier classes in algebra. So basically what I've written here, useful factoring method, and then I just put boxes around these. So the idea is, you might be thinking, well, factoring is good, right? But we can at least look at this particular result here, this theorem, this lemma, and know that we may not always be able to do this. And so if we can't, there are other methods that we can rely upon to get to an answer. So for instance, you may start to factor something and find that you can't get 1 and 2 to work, okay? So then you're not stuck, you'll have other methods. But in mathematics, especially in calculus, the ability to factor is very important. And so we need to be able to improve our methods of factorization. And then, of course, when we get to theory of equations, we'll be able to look for all zeros of polynomials and then be able to write the given polynomial as a product of first-degree factors. So that'll be an interesting method that we learn later. So let's apply this method here and solve, as I say here, in R by factoring. Now, of course, as we've stated here, X can be imaginary, but in this section, we will try to stick to the values of X that are actually real. And then in the next section, venture into the interesting problems where X can take on imaginary values. So notice here, we have A equals 3, and we have C equals -4. So again, notice it is important that we write this in descending order so we can compare it to the statement of the theorem. So again, A is 3, C is -4. So now this implies AC equals 3 times the -4. Now, one thing we want to notice here is that there's no need to move forward until we check to see what we have initially. If we look at the sum here of 3 and -4, we get -1, and that's clearly not 4. So what we want to do is redistribute the numbers, hoping that we can actually find a good Z and a W. Notice here that we think of the 4 as being 2 times 2, and then the 2 times the 3 is a 6, and that would put us in the right direction. So notice first here, we'll think of 3, and we'll think of 2 and a -2. So we simply break down the 4, the -4, into 2 times -2, thinking about prime factors. Now what we can do is we can move the negative into the 3 times, or actually leave the negative with the 2, and then multiply the 3 and the 2. So that gives us a 6 and a -2. Now, of course, there's nothing wrong with whatever method you use. You don't have to jump to the right answer instantaneously. If the process works, you will be able to combine the numbers in a way to get the correct Z and W. So don't worry that it may take you a little while just to redistribute the numbers. That is the basic trial and error part of this method, but it is something that you can control. And it's a little bit more efficient in the sense that you can mix and match prime factors in a way to get to the desired Z and W. Now, at this point, you might be thinking, does it matter which one of these numbers we assign Z and W? Well, before we jump to that, let's just now see that this actually is good. If we think of the 6 as a Z and the -2 as a W, we see that the sum is actually 4, and that's good. So again, we can set Z equal to 6 and W equal to -2. And then again, it does not matter. It does not matter if you do the opposite, set Z equal to -2 or W equal to 6. That will not matter. So don't worry about that. So we just put a box around this and say that we have the desired Z and W. And now the theorem allows us to use these numbers to factor by grouping. You can actually set up this theorem with formulas and just fill in the Z, the W, and the C into the formula, which is fine, but that's just another formula to remember. And we have to know enough formulas anyway. So what I would suggest is just now use a factoring by grouping. So this implies we'll have 3x squared plus 4x minus 4. And now, because of the B equals Z plus W, we can rewrite the middle term using the Z and the W. So this gives us 3x squared plus 6x minus 2x. Now, of course, you can trial and error everything, but this method is very efficient and very systematic, and it's easy to carry out. And it's also a method that you can teach, and individuals will tend to remember this method. And that's what's important, as the numbers vary in size. So now what you can do is factor by grouping. So we can look at the first 2 terms and the second 2 terms and move the problem forward. And again, how you factor, again, is up to you. There's plenty of flexibility in this method. So now we notice in the first 2 terms here, we have a 3x common to both. So we'll factor that, 3x. And this leaves us with an x plus a 2. And now here, the idea, what forces us to choose the correct factors here is that we now need an x plus 2, so we can factor the -2 from each of these terms. So we have plus -2 times an x plus 2. Now, of course, just visually go back and check that you get exactly what you had on the previous line, 3x squared. And in this case, let's just see what we have. Yes, the 3x times the 2, the 6x. So this checks out. Now, the whole reason that this works is that we've got the common factor here. And so we can now factor that. So this is called factoring by grouping. So x plus 2 times what remains 3x minus 2. So now you see that these are sufficient conditions. That is, if we do have the existence of the z and the w, then we can actually write the primitive quadratic polynomial as a product of two first-degree polynomials. So this gives us an algorithm to do this. Now, of course, not all integer polynomials will have this property. And again, that doesn't mean that we stop. It just means that we have to apply other methods. And so the beauty of the quadratic equation is that we can always solve it. Its theory never forsakes us, so to speak. So now we can finish the problem. So the original problem was to solve 3x squared plus 4x minus 4. So now we will replace, in this case, the 3x squared plus 4x minus 4 with this product. So equivalently, we have x plus 2 times 3x minus 2, the good old distributive law, equals 0. So an equivalent equation to this equation is this one. And now, of course, we have the 0 product. So 0 product. A very useful result. So we can set each factor to 0, or you could just do a little visual, but it's good to write this down. So x plus 2 must be 0, or 3x minus 2 must be 0. That is, remember, the 0 product says at least one of the factors must be 0. And what we're going to see is that with each factor, we get a different value of x. So in the first case, we get x equal -2. And of course, now that you're thinking you could factor this even more and get the answer, but let's just go ahead and do it the old-fashioned way. So we have 3x equals 2. So x is 2/3. Of course, if you remember what we did with the linear equations, we factor the 3, we have 3 times x minus 2/3, and you get the same response. So however you want to do it, this way or this way is certainly fine. So now we see again that by factoring, we see that the value of x equal -2 and also the value of x equal 2/3 are actually solutions. So this would imply, and then of course we have no reason to discard either of these because there's no problem with any division by 0 or anything of that nature. So we're good. So now when you do your solution set, you have -2 and you have 2/3. So I would encourage you to practice factoring using the AC lemma. It is a good method to improve just your understanding of working with numbers. We like to break down numbers and look at their factors. And then by doing that, you get more efficient at negotiating the numbers. Now, again, just remember, if this process does not provide a simple method to actually get to these Z and W, or it's impossible, then that's fine. You can just say, all right, I can check other methods. Now, I will say this, there'll be a way to test whether or not this method works when we talk about the quadratic formula. So don't think that this is something that you have to do every time. If the problem requests that you use factoring method to solve the quadratic, then you can be assured that it will factor with that method. But just remember, now we're going to investigate other methods. But like I said before, practicing this will be good and it will make you better at solving equations in general. So let's look at another method. Now, one thing we'll notice, and if you looked at the integer polynomial before, if we have an absence of an x term, or we have a completed square and a constant, then we have a very simple situation. So what we want to do now is called the square root method. And what it means is that we have an expression, maybe a real expression. We'll start with that. So we'll just say, suppose U is a real expression. We could certainly have it to be complex with imaginary coefficients, but we'll just stick to real expression for now. And we will let A, in this case, it can be any number. We could say maybe a complex number or even a real number. Let's just say complex number, which is fixed. So again, remember, when we fix A, we mean A is constant. So let me just write this here. A is constant. So now the equation looks like this. So we have U squared minus A equals 0. Now, of course, remember, oh, and I have to move around to keep the lights on. U can be just a single variable, X, or it could be a combination of other terms that is squared. So we are very flexible with this particular result. So the nice part about the way this is written, looking at the previous problem, we have what we call a quadratic term that could have many forms. Here, we have no U term, so to speak. We don't have the first power of the U expression, but we do have the constant. So when we look at this, we think of this as simplified. That is, there is no U term. And the absence of the first degree term in U makes the solution here very simple. And what we can do is now utilize the difference of two squares. That is a factoring method. There are many ways to look at the square root property, but since we've been factoring, I just want to go ahead and look at this in terms of the difference of two squares. Later on, we'll talk more about absolute value and how we can use that to our advantage. But right now, what we're going to do is we're going to rewrite A as the square of the square root of A. So this is a little bit of smoke and mirrors as we move this problem forward. So let's rewrite A as the square root of A squared. So factoring is really important. We have to factor as we continue through STEM mathematics. So these are good techniques. And now what we notice is we have the identity. And let me just remind you over here, I'll just use A's and B's. A squared minus B squared. That's how we notate the difference of two squares, where A and B can be expressions or constants. So we have A minus B times A plus B. Again, we talked about that in our previous lecture. So now we can factor using this identity. So equivalently, we have U minus the square root of A, and then U plus the square root of A equals 0. Now, when you think about this particular setup and you refer to the last problem, this is now the zero product. And then, of course, this requires that at least one of the factors be zero, using properties of real numbers. So if and only if u minus the square root of a equals zero. So again, you can look at this and do it in your head, but let's just go ahead and write this out formally. So by zero product, at least one of these is zero. So we have u equals the square root of a, or u equals the additive inverse of the square root of a. So now what we have are two values which we expect for the quadratic, but it's a much simpler method. Again, this is a specific type of an equation, but we don't have the AC limit to worry about. We have a much simpler method. Now I will say this, every time you work an equation, do not hesitate to be creative and apply whatever method you like. As long as it's a legitimate mathematical method, then you should arrive at the correct response for the values of the unknown. So equivalently, now we can just save a little bit of time. Not all homework systems will have a plus minus. So if that's the case, then many times you have to put solutions separated by commas, because the plus minus symbol is not part of the homework system or the computer algebra system. But we can just say now, just to consolidate for your notes, plus or minus the square root of a. So now with the square root property, we have a very simple solution. And so just remember, this is more restrictive, but if we have this form, then we have a very simple way to get to the punchline, which is right here. So once we have this, then we can undo the expression u if it is more than just a variable, and isolate the variable. So very, very useful technique. So let's look at an example that utilizes this. So here's an example from your notes. So we have 4x minus 1 quantity squared minus 16 equals 0. So if we look at this, this compares to our original form. We have an expression u, which is 4x minus 1, and it's squared, and then we have the constant term. So like I say here, there is no u term. So this means that we can use the square root method. Now, I want to encourage you to look for these patterns, because you could certainly expand this and then you have a quadratic equation, but it's more complicated. So do not overlook the fact that if you have the quantity or expression squared and the constant term, allow it to move forward using what you know about the square root method, because it's much simpler. Sometimes we do additional work, and that's not a problem, but we certainly don't want to do that here. So now with the square root method, equivalently, we just go to the punchline here. This is the result of our work. So we have 4x minus 1. So to the side here, just to be clear, we can just say that our expression u is 4x minus 1, just to compare it to the method we have here. And this will equal, again, when we transpose, plus or minus the square root of 16. So basically what I'm mimicking is the result right here. So we have u equals plus or minus the square root of a, just like we have up here, and we move down to here. So again, a is 16, and we have u is 4x minus 1, so u equals plus or minus square root 16. That's it. So now, of course, this will give us two cases. So we could just say, for instance, case 1, let's just take the positive square root. So we have 4x minus 1 equals the positive square root of 16. Again, that's a nice number. That's just 4. And then, of course, this is an easy solution. So we have 4x. Let's add 1 to both sides, and we get 1 plus 4, which is 5. So x is 5 over 4. Now for the other or, we use the negative radical or the additive inverse. So we have 4x minus 1 equals the additive inverse of the square root of a. So that gives us negative 4. Now, of course, when we solve just by using the simple methods we learned, we'll add 1 to negative 4 to get negative 3. So x equals negative 3/4. So now what we see, just like we had before, we can place these in the solution set. 5 over 4, comma, negative 3/4. So be vigilant about the square root method. Again, we look for this form. And if we have that form, then we can move to a very quick answer. It does mean that we may have to negotiate some algebra with each case, depending on the complexity of the u expression. But you see how elegant this is by just basically focusing on the difference of two squares to get a very simple solution right here. Okay, so this will be a good method to use when indeed it applies. Now, let's look at another method. As we think, okay, well, number one, we can factor. Number two, if we have a specific form, we can use square root method. And when I say the first one, when we can factor, that means we've got the primitive polynomial where we can find a z and a w. And the primitive polynomial is fairly specific. And you're thinking, wow, you know, if we don't have something that fits those patterns, what are we going to do? Well, one method is to complete the square. That is, you noticed on the last problem that when we had the completed square, so to speak, we had u squared. That made the problem very, very simple. So what we would want to do is just take the general quadratic equation and produce the square term. So we have the square term and the constant. And that is possible with quadratic equations. Now, what we can also do is think this way. If we complete the square using the A and B, C symbols, then we would produce a formula. And that formula is called the quadratic formula. So you might be thinking, we could use the method of complete the square to solve a specific problem, but then we're thinking, well, we could just use a formula and substitute the A and B and the C. Now, I will say this, there will be times when completing the square is a method that's required for certain forms to be used, for instance, in an integral formula or working with conic sections or whatever. So we don't always think that the completing the square is a waste of time. It really depends on the context of the problem. So let's look at this, complete the square in the general situation. So if we complete the square in the general situation, you could always apply this to any specific quadratic polynomial. And if the problem did not require a particular method, you're thinking, well, I'll just use the quadratic formula, fill in the values, and be done. So just remember, problems will sometimes require a particular method, and other problems may just say, solve the equation, and then you can choose the method. So now what we're going to do is, again, to have a quadratic, the a must be non-zero. Clearly, we have to have a squared term. So what we're going to do is suppose, because we can always do this, suppose that the a is positive. That's going to help us when we consider square roots. And sometimes we say WLOG, and that means without loss of generality. Without loss of generality. Because if you're working with an equation and the a is less than 0, you can always multiply the equation by -1 to convert the number less than 0 to a number greater than 0. So that's why we say without loss of generality, because it will not change the solutions. I mean, we use that technique, without thinking about it when it comes to solving equations. What we do to one side, we do to the other. So this would not change in any way the solutions. So we can actually insist upon this without weakening our result. So now this will give us ax squared plus bx plus c equals 0. Now this method you can use to complete the square anytime. So not only are we going to get a formula out of this, but we will also get the method to complete the square, which you should know how to do. Now, in order to do this, we have many methods available, but I'll just do this a way that's easy to replicate. Now, what's important is we have to focus on completing the square with the x terms. So we're going to isolate the x terms. So we're just going to subtract the c term from both sides to write this. Now, one thing that's very important with completing the square is that we need a monic polynomial. Monic means that the leading coefficient is 1. So at this point, we will need to factor a on the left-hand side. And you're thinking if the a is 1, as we've insisted, if that's the case, then factoring the 1 would not be required. But we're doing this in general. So we have a x squared, and then of course we have to compensate by dividing the b by a. Again, we may basically multiply b by a over a, but leave the a in the denominator and extract the a in the numerator. And so now we have an equivalent situation here. Now, in order to complete the square, so I'll go ahead and just close this off, just so we have less steps to make it this clear. At this point, we see that all of these equations are equivalent. And I don't want to rush through this. So now, notice this is monic. So we say monic coefficient of x squared is 1. Monic means precisely what I've written here, and that's very important. So now, how do we complete the square? Well, this is the easiest part. What we do is we take 1/2 of the coefficient of the x term and square it. So we go here, and it really depends on your numbers as to how complicated the b over a is. So we take b over a, and we multiply by 1/2, and we square it. That's how we determine the number that is required to complete the square. So we're thinking of the perfect square formula when we think about doing this. And I'll write that formula down. That is this is what's driving everything. So I'll use uppercase letters. A plus B quantity squared equals A squared plus 2AB plus B squared. So that's a very useful identity called the perfect square. Perfect square. So students often wonder why we do what we do when we complete the square. Well, it's based on that identity. So now of course we can finish this off. So we square the B. And then of course the 2 times the A squared is just 4A squared. So this is the number that we must add to these 2 terms to create a perfect square trinomial. But of course, if we add this number, we also need to subtract it. Now, since we're dealing with an equation, what we can do is just add the same number to both sides, and we still have an equivalent equation. So this number, as we will say, completes the square. So at this point, we do exactly that. We'll just go ahead and add this to both sides, or add and subtract on the same side, depending on how you want to work this. So we have A x squared plus B over AX plus B squared divided by 4A squared. Now, this is where we have to be a little bit subtle. So that's been added here, but notice when we add the number here to this expression in the parentheses, we now have to remember the A that we have here. So this A will absorb one of the A's here. So basically what we've added to this side is B squared over 4A. So when we go over here, we do B squared over 4A minus the C. Okay, so that makes the difference. So now, again, remember, we look at this, and this is the perfect square, just like we have here. Here is the perfect square. Perfect square. So remember, when we do our algebra, since we factored here, we have to be very careful as to what we need to do. Now, the reason I'm doing this, you're thinking, well, we could just divide by the A and have it over on the other side or whatever. But I want to show you some techniques that will help you when you start dealing with functions. So I varied my procedure a little bit just to keep you vigilant about what we're doing. So now we're in very good shape. So we have equivalently A, and now we'll use our formula here. We have our A and our B, in this case with the uppercase here. So we have an X plus the square root of that term, which is B over 2A, quantity squared. So now, again, we've got this here based upon the letters that we're using here. And then if you like, we can just get a common denominator. 4A, B squared, and then of course, multiply the C by the 4A, so we get minus 4AC. So again, the perfect square turns out to be quite useful here, but we don't have the same elegant formula for third degree polynomials or fourth degree. I mean, polynomial formulas are possible, but they're very, very complicated and not extremely useful. But with that said, that was the opening of Galois theory, where they basically determined that if you're interested in higher level formulas for higher degree polynomials. They just don't exist, which is probably a good thing since the ones for 3 and 4 are so complicated that they don't provide much help to us. So again, when you look at this, we're thinking we're pretty much ready for the square root property. We just need now to divide by a. So we have x plus b, and remember, I varied this a little bit just to give us some practice working with algebra. There are many ways to write this. So when we divide by a, we get b squared minus 4ac divided by 4a squared. And so now we can use square root property or square root method. So now this is like we had before, like we had the u squared equals the a, but now the a is kind of complicated. So we have plus or minus the square root of this. So by square root, we get x plus b squared over 2a. Oh, sorry. I've got all these squares here. Yeah. No need to have the square there. Sorry about that. That's just b over 2a. When we took the square root of this, and I spoke it right, but I wrote it incorrectly. So please fix that. Will be plus or minus the square root of b squared minus 4ac divided by 4a squared. Now this is where it's convenient. Notice when we take the square root of the quotient, we get the quotients of square roots using our laws of exponents, but the square root of 4a squared would simply be 2a because we have presupposed that a is positive. So now when we do the square root of 4a squared, this by definition is 2 times the absolute value of a, but a is positive. So we're going to get some work with absolute value, and I'll say a whole lot more as to why this is true. But that's the convenience that we had at the beginning because a was positive. Again, that just makes our work a little easier. We don't have to deal with so many pluses and minuses. Now to finish off, just to complete the step, all right, what we have here, we have x plus b over 2a, no square, of course, equals, we have plus or minus b squared minus 4ac, and then, of course, downstairs, as I just noted, we have the 2a. So now we can transpose the b over 2a. So x equals the opposite of b over 2a, or the negative, plus or minus the square root of b squared minus 4ac. Again, using that plus minus symbol, which isn't always available. But now, of course, we've got the same denominator, so no more work is required except just to, if you like, write it as one fraction, which tends to be the way it's written. So the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So now what you see here is a formula that's actually usable. A relatively straightforward formula that's not overly complicated, which turns out to be quite a gem when we're dealing with quadratics and functions and formulas and equations in quadratic form. So now you can see that if you attempted the AC lemma and you were having no luck with it, you might be thinking, oh, okay, if I look at b squared minus 4ac, it must not be a perfect square, because the only way the AC lemma can work is that we actually deal only with what? Rational numbers, which are ratios of integers. And of course, if the b squared minus 4ac is not a perfect square, then there's no way that the AC lemma is going to work. So this quadratic formula actually provides more interesting information than we maybe initially expected. So note here, we'll say AC lemma, here's another requirement, requires that b squared minus 4ac is a perfect square. So that limits things. So maybe you're having no luck with the AC lemma, and you test this, but you find it's a perfect square. So then you got to go back to the drawing board and rearrange the numbers and combine them in the right way. But if you use this b squared minus 4ac and you see that it's not a perfect square, then you stop. Okay. And additionally, we can see the following. Number one, b squared minus 4ac is a positive number. It could be a perfect square, but say it's a positive number, then this implies that we have, in this case, two distinct real zeros. To emphasize the fact that there are no imaginary zeros here. If the argument of the square root is a positive number, then its square root is real. Okay, what else could happen? Well, it could be the case that b squared minus 4ac is 0. So this is using the law of trichotomy of real numbers. So this would imply a repeated 0. So repeated zero of, well, that just leaves us minus b over 2a. That's it. Because, of course, if this term is 0, then the only thing that's left is the opposite of b divided by 2a. And boy, that's really simple. And when we say repeated, that just means that we get the perfect square. Okay, so the key here is that we think of repeated meaning that we've got a 0 of multiplicity 2. So we could think of this as another way of saying it using the theory of equations. We have a 0 of multiplicity 2. And I'll say more about that when we get to theory of equations. A 0 of multiplicity 2. Students like that because that certainly simplifies things a great deal. And now, of course, the third case would be, because we know real numbers fall into 3 categories, we now have to consider the fact that the b squared minus 4ac were less than 0. So now what we're seeing is that the first 2 cases would be something that we might see in the problems we're working now, and as you work your homework. But we're going to have to wait to the next section for this, because this will require us to do some review and also some introduction of terms for imaginary zeros. So notice now, if the b squared minus 4ac, that is the argument of the square root is less than 0, then the square root that results is an imaginary number. So this would imply, and we get even more information. We have 2 distinct imaginary zeros, or in the speak of theory of equations, we get 2 complex conjugate zeros. And what that means is this plus and minus that we have from the formula will give us complex numbers, which are called conjugates. Now, there's a certain amount of vocabulary here, but what it means is that if you have real polynomials and you have an imaginary zero, then automatically you get that the conjugate of that complex zero or imaginary zero is also a solution. We'll say more about that too. So there's a whole lot of theory going on here that we're going to investigate more as we move through the class. But for right now, I'm just trying to open the door to that. So at this point, we can use this classification to at least say these are the types of zeros we expect. And of course, as you do higher order polynomials, you can see that you could have quadratic factors there, which you can easily analyze and hopefully be able to get some reasonable analysis of what's left over. So again, think of this analysis as something that's very simple. Now you've got to be thinking that we call this b squared minus 4ac a name, and it has a name. It's called the discriminant. So a lot of times when you're working with conic sections, you deal with the discriminant when you're trying to classify conic sections. But what's important here is that even if you don't give it a fancy name, b squared minus 4ac is going to stick in your head. And so now you can at least, for instance, if you're analyzing a problem, a quadratic an equation, then you can, before you do anything, you can look at the b squared minus 4ac and figure out what you're going to get. So if you know that the discriminant is negative, you're going to go directly to the quadratic formula. No reason to bother yourself. You know, if you see this, then of course you're going to check for perfect square. Then you probably say, well, I can factor this. But if it's not a perfect square, then you go right to the quadratic formula. And then of course, if it's zero, then you just got minus b over 2a, and that's it. That's the number 2 is the easiest case. The repeated zero, the zero of multiplicity 2. So again, just remember that with the formula for the solution of the quadratic, you get plenty of information. So again, when it comes to dealing with quadratic equations, we can always solve them. There's nothing that's going to keep us from solving the quadratic equation. So now let's look at a couple of examples with the quadratics. Now again, like I said before, it is up to you how you want to distribute numbers. So what I'm going to do, I'm going to take a problem here from your lecture notes, and we're going to solve it. But I want to give us practice just completing the square again, using maybe just a little bit different approach. It's basically the same approach, but you're thinking you could just use the quadratic formula. But the reason I want to do this is because when you do the derivation, and it's not monic, you have to factor. So we see this is not monic. I mean, if I do one that's monic, then that doesn't give you much practice. So I'm going to flip these problems. So we'll say this: solve the equation to get practice. Solve the equation by completing the square. Now, I always tell students, if you can complete the square, then using the quadratic formula is very simple. So first, what we're going to notice is that it's not monic. So let's go ahead and write an equivalent equation. So just go ahead and take the 7 over. Now, remember before, this is your choice. And so you can look at this and say, well, I can factor the 3 because this is not monic, and then eventually just go ahead and divide by it to get it out of the way. And that might make your life a little bit easier. But notice when I did the derivation, I left it over there. So you had to make the adjustment. So at this point, you can go ahead and divide everything by 3. So you have x squared minus 5 over 3 x equals 7 over 3. So this is the same thing as just factoring the 3, but instead of leaving the 3 multiplied on this side, I just went ahead and just divided everything by 3 to get the same result, an equivalent result, which you could have done if you do the derivation a different way from what I did. But there's no variation. It's that when you deal with functions, it's probably easier to do the method of the factoring because you really don't have a right-hand side when you're dealing with a function alone. You don't have the equal to 0. So now we can say this is monic, and we want the number that we have to add. So we're going to take half. We're going to take half of this coefficient. Let me put a little box around it. Less than 0, but that doesn't matter. When we square it, the negative goes away. So we're going to do negative 5/3 times 1/2. Remember, we take half of it and then we square it. So of course, negative 5 times negative 5, that gives us a 25. And then of course, the 2 times the 3 is the 6. We square it, we get a 36. So this is the number that we have to add. Now notice now, since we divided, we just simply add this number to both sides, and there's no division like we did with the derivation. So go back at that and look at that and see how, by the way I did it, we had to make an adjustment in the derivation. So we got it. So let's do it. So now we have x squared minus 5/3 x plus 25 over 36 equals, now do the same thing, 25 over 36 plus 7 over 3. Now the numbers aren't so user-friendly, but that's okay. Everything's good. Notice now this is the perfect square. This is the 5 over 6 when we square root it, just like I did before. And remember, I left the square on the b, which we don't want to do this time. So now, equivalently, we have x minus 5 over 6 quantity squared. So now notice when you multiply these and hit it with the 2, you get the negative 5/3 x using the perfect square formula. Now we have a minus instead of a plus. So we have to be flexible with our completing the square. And now on the other side, we just want a common denominator. Notice here, we can do this. Let's go ahead and write this in a suggestive way. 36 is just 3 times 12 plus 7 over 3. So again, by factoring this, we see that we need a 3 in the common denominator, and we also need a 12. So we have 3 times 12. 25 doesn't change, but that gives us plus 7 times a 12. So we have 25. And of course, 7 times 2 is a 14, carry your 1. That gives you an 8. And of course, let's go ahead and write the 3 times 12 is 36. That's a perfect square. And so now we get 109. 4 plus 5 is a 9. And then, of course, the 10. That's easy. So that gives us basically the constant on the right-hand side. So now we can apply square root method. So equivalently, x minus 5 over 6 equals plus or minus the square root of 109 over 36. Now, one thing you've noticed here, and this is how I basically teach this, when you use the quadratic formula, you compute the discriminant first, then substitute into the formula. when you're using all of this, you don't go ahead and apply the square root method and then do all of the algebra under the radical. That's a waste of time. Go ahead and do the computation to arrive at the one response here, the one number. And then when you do the square root method, it's much simpler. So now we're good to go. This will give us plus or minus the square root of 109 divided by 6. Okay, so now equivalently, x, adding 5 6 to both sides, plus, well, let me do this. Plus or minus square root 109 over 6. Now, if you want, you could write this as one fraction. That really doesn't amount to much. 5 plus or minus the square root of 109 divided by 6. But now, of course, if your computer algebra system doesn't have a plus minus, this will now give us 5 plus the square root of 109 divided by 6 as one solution, and then the negative radical, 5 minus the square root of 109 divided by 6. So one thing I want to, again, mention here is that when I did the derivation, I just left the factor of a here. I didn't divide by it. So when we added the number here, we had to compensate by the fact that I had not divided by a. So that's really the number that was added to both sides. Here, notice, I went ahead and just divided from the very beginning. So that's a technique you can use if you like, if you think this is a little bit easier. It really doesn't matter. But when you're dealing with specific numbers, maybe you'll find this to be a little bit easier. So the key to completing the square, you might think, boy, I don't really want to complete the square if I'm just solving a quadratic equation, because there's really no need for it. Now, like I said before, completing the square has many uses in your classes as you continue in college algebra, pre-cal, and the calculus sequence. So there'll be times when you need to complete the square, not because you're trying to solve an equation, but you're trying to produce a form that gives you more information. Maybe, like I said before, you're dealing with integrands that are Pythagorean. You're dealing with conic sections, again, that are Pythagorean. So the key is that just practice this so you are comfortable with the process, so that you remember when you complete the square, regardless of the problem, you must achieve the monic polynomial. Either you factor it and leave it right, the constant, the a out here to the side, or you divide depending on the context. And then you complete the square by taking half of the x coefficient and squaring it, as we've done here. So that part of the process is important, and this is what you need to make sure that you master. Now, as a final problem, and this is important, let's just look at solving an equation with the quadratic formula. No complete the square. We just give an equation, and you're told use quadratic formula. So here, example, solve using quadratic formula. And here's an equation. It looks pretty harmless. X squared plus 4x minus 10, well, I need my x, minus 10 equals 0. X squared plus 4x minus 10 equals 0. Now, when you look at this, again, the key to using the quadratic formula lies in one first step. That is, make sure you have standard form. Notice all the problems we've been working on have given us the standard form. What is the standard form for using the quadratic equation? You need ax squared plus bx plus c. Now, of course, a, b, and c can have any sign you like, but this is the standard form. So if we are going to apply the formula, then we must have a form where we have the zero, and then we know that we've got the coefficient of the x squared term, we've got the coefficient of the x term, again, a, b, and then we have the constant, which we call c. Again, these are standard letters, so it doesn't matter. I mean, you can always change them up, but this is universal. So now what we do is first, always, let me write this down. Compute the discriminant first. Always. Sometimes students want to just substitute all the numbers into the formula, trying to do the arithmetic, make mistakes. Focus on the discriminant, and then you can move the problem forward knowing what types of solutions you're going to have. So the discriminant, let me just write what it is. It's b squared minus 4ac. So over here, I'm just going to write a, again, we've got standard form is 1, b is 4, and c is -10. Right there. So that should be something that you write in your work. And then b squared, so we have 4 squared, then we have minus 4 ac. Now, remember, numbers can be factored, I mean, clearly, just like the letters, and we want to practice with that. So notice we've got subtracting an additive inverse. That by definition is addition. That is, if you subtract the additive inverse, or the additive inverse of the additive inverse absorbs the negatives. So again, a property that you learned in Algebra 1. So this gives us 4 squared plus 4 times 10. Now, at this point, you could just simply add these numbers. And we're going to do this 2 ways. I'm going to add the numbers, and then I'm going to factor it because I want you to be able to factor well. Notice this is 4 squared, which is 4, 2 times 2. And this is 4 times 2 times 5. Because 10 is 2 times 5. And then so now you're thinking, well, we've got common factors here. We have a 4 times 2 here and a 4 times 2 here. Those are both 8. So we get 8 times 2 plus 5. Well, that's 7. So that's 8 times a 7, which is a 56. Now, what's interesting about this is that what we should do is just kind of stop with that. I mean, that was kind of a waste of time for me to do that, really. Let's just back up. That was a waste of time. 7 is a prime number. 4 is a perfect square. So this gives us 4 times 2 times 7, which is 4 times a 14. And you're thinking, Professor Wallace, why did you do that? Well, let me show you. You can do this many different ways. But if you add the numbers, then you're going to think about doing a factor tree. So the alternative situation, for instance, had we done this, we could have thought, well, that's just a 16 plus a what? A 40. And that's 56. Okay, we'll get the same thing. Of course, we'll get the same result. But now notice what I've done here. By factoring, and you're thinking, well, I could have just pulled out the 4 because that's the perfect square and just left it that way, and instead of pulling out the 4 and the 2, but that's what I did. And so now when I moved to this point, the first time I thought I wrote the 46, I'm like, no, that's a waste of time. What's the perfect square in this? 4, like we see here. And then you're left with the 14. And now when you take the square root of this, the square root of 4 is 2. And of course, the square root of 14, you just leave as the square root of 14 because you need an exact answer. But notice this is a useful expression, because it gives you a factor which is a perfect square and then a non-perfect square, and this is positive. So of course we would have known that the AC lemma would have never worked. And then of course this gives us 2 distinct real zeros. The idea is that as you look at the discriminant, you may adjust things and then say, okay, let's write this in a way so I don't necessarily have to do a factor tree. So when you look at it this way, you can now easily square root things. So do all of this work first. And then we have x equals the opposite of b plus or minus the square. I'm just repeating the formula here so you'll remember it. Maybe you don't want to write it again. 2a. So now we have the opposite of b, which is -4, plus or minus. Now we can easily square root this. That gives us a 2 times the square root of 14 divided by 2a. 2 times 1 is 2. Now this is where we need to be careful. Notice there's a 2 here and there's a 2 here. They absorb. So the -4 is just -2 times 2. So when we look at this, the 2's all absorb because they are factors for all of the terms. So now that leaves us with what? A -2 plus or minus the square root of 14. That's it. They've got a 1 downstairs. So now equivalently, we can write -2 plus square root of 14, and then -2 minus square root of 14. Now, what's important about what I've done here is not that when you work the problem, you're going to just boom right to the correct response. As you work the problem, you'll make adjustments. Lots of times when we work our calculations, we'll slip up somewhere, and then as we work, we'll say, oh, wait a minute, that should be that, make the correction. Because you put in enough steps so that everything is consistent, so that one step logically follows into the next step. So let me repeat what I've done here and emphasize that in order to do good mathematics when it comes to college algebra, pre-cal, and calculus, is we have to focus on the basics. So when you're using the quadratic formula, compute the discriminant first. Standard form, a, b, and c, b squared minus 4ac. Maybe the numbers are not nice, and so you might be in a chemistry class or a physics class, and there's no hope of a perfect square, so maybe you don't worry about it, okay? But still, you want to compute the discriminant. We've got fairly nice numbers, so we compute the discriminant just by looking at some factoring. Factor the numbers, and then we expose a perfect square, 4. And then the non-perfect square factor, 14. So we have a positive discriminant, so we get 2 distinct real zeros. And now we can use the formula where we can easily substitute the square root of the discriminant, because we can easily take the square root here and get 2 root 14. Plus or minus, we have the opposite of b and 2 times a. And then we look for additional common factors. Now, of course, if we didn't have a 2 there, then we couldn't break this up the way we did, but very convenient numbers. We have a 2 here, a 2 here, and a 2 here. So all of these absorb. And so when you want to show that you are absorbing factors, put boxes around them. That way you can easily see what you've done. The slash lines are a waste of time Why? Because it covers up the work. This simply highlights what's common to everything. And then you can say, okay, what's left behind? -2, plus or minus 14, and nothing but a 1 downstairs, so you don't have to put a 1 if you want. I mean, you could, but it's not necessary. So when you look at this, you're thinking, whatever method you choose, maybe you've got good numbers where the AC lemma works, it doesn't matter. You can always solve a quadratic equation or an equation in quadratic form, because the theory of the quadratic equation or the theory of the quadratic function allows that. And that's a luxury. We of course are always happy when we find these types of equations in front of us, because we can jump to the solution. We can work to the solution and know that we have good mathematics. Otherwise, when we have to apply other theory, we get to calculus, we may have to apply some numerical methods. So just remember, the methods that we learn in college algebra are extremely important, and they will be carried with us throughout. So take the time to understand the quadratic formula. And then, of course, you'll see some examples where you'll be given a function from an applied type problem where you basically just have to solve it using whatever technique you like. So I will assure you that if you can do this, then those problems will be fun and less demanding. Okay? So we are done. Thank you.